A human heart can beat perfectly for decades, and then, in a matter of seconds, spiral into a fatal, chaotic spasm. That violent disruption rarely starts with structural damage. It usually traces back to a single microscopic shift in electrolytes. The central operator in this electrical system is potassium. It is the principal positively charged ion, or cation, inside your cells, and its careful management is what keeps cardiac tissue electrically stable. Your body hoards potassium in a highly asymmetrical way. 98% of it is locked away deep inside the cells, roughly 3,400 millimoles. The remaining 2%, barely 80 millimoles, floats in the extracellular fluid outside. This diagram shows exactly how that extreme divide is maintained: the sodium-potassium ATPase pump. Working continuously against the natural concentration gradient, it actively pushes 3 sodium ions out of the cell while pulling 2 potassium ions in, consuming ATP energy with every cycle. Because that outside pool is so incredibly small, it creates a dangerous clinical trap. Even a tiny numerical shift of a few millimoles in the blood drastically alters the ratio, causing a massive, disproportionate impact on the overall excitability of the heart. To prevent those tiny shifts, the body relies on strict homeostasis. We consume 75 millimoles of potassium daily through our diet. The kidneys handle clearing it, taking responsibility for 90% of all potassium excretion. This transcellular gradient, the ratio of internal to external potassium, is the defining factor that sets the resting membrane potential. Because potassium naturally tries to leak out of the cell down its concentration gradient, it takes its positive charges with it. This ongoing outward leak is what leaves the inside of a resting cardiac cell electrically negative compared to the outside environment. So the baseline relies on a clear chain of command. The kidneys regulate the macroscopic potassium load, which establishes the steep internal to external gradient, which in turn locks the cell into its essential negative resting state. This 5-phase action potential graph is the electrical blueprint for a heartbeat. The descriptions below reveal where potassium takes control. During the phase 2 plateau, the rapid phase 3 downward slope, and phase 4 stabilization, outward flowing potassium dominates. Potassium's primary mechanical role in this cycle is repolarization. It drags the cellular voltage back down to baseline, resetting the machinery so the heart is prepared for the next beat. When serum potassium drops below 3.5 millimoles per liter, the patient enters hypokalemia. The immediate mechanical consequence is hyperpolarization, where the resting membrane potential drops, becoming even more negative than normal. As shown in this threshold model, the resting membrane barrier drops significantly lower away from the trigger point. This makes the cell physically harder to stimulate, suffocating the electrical conduction and slowing the heart's reflexes. This chart displays the cellular delay. Notice the dotted line stretching outward. With less potassium exiting, repolarization crawls, stretching phase 3. This hesitation leaves distinct physical markers below: a prominent U wave, a cup-shaped ST depression, and a flattened T wave. This extreme depletion typically happens for 2 reasons. Either the body is physically losing potassium through heavy renal flushing and severe digestive losses, or alternatively, the potassium in the blood is being rapidly transferred inward and hidden away deep inside the cells. To summarize the low end of the spectrum, a lack of potassium hyperpolarizes the membrane, severely limits cellular excitability, and generates a diagnostic U wave. On the opposite extreme, when serum potassium climbs above 5.5 millimoles per liter, it triggers hyperkalemia. Instead of dropping, the transmembrane potential decreases by moving closer to zero, pushing the cells into a highly volatile state of hyperexcitability. Returning to the threshold model, the resting barrier now shrinks upward. Because the resting voltage is resting dangerously close to the trigger point, even the weakest premature stimulus can force the cardiac cells to misfire. This chart section highlights how this volatility prints on an ECG. The initial warning is a distinctly tall, symmetrical, and peaked T wave, which is quickly followed by a hazardous widening of the QRS complex as the internal conduction pathways degrade. Before responding to these signs, clinicians have to navigate a common diagnostic trap. True hyperkalemia must be distinguished from pseudo-hyperkalemia, a false elevated reading caused by red blood cells breaking open and spilling their massive internal potassium stores simply because of a rough blood draw. When confirmed, a true potassium surge often indicates massive internal tissue damage. Severe traumas like rhabdomyolysis or extensive deep burns crush millions of cells simultaneously, dumping their vast internal potassium reserves directly into the bloodstream. The summary for the high end: excessive potassium creates a state of hyperexcitability, prints a dangerously peaked T-wave, and puts the patient at an immediate risk of sudden cardiac arrest. Placing these two extremes side by side clarifies the physical divergence. Hypokalemia drags the electrical voltage down into a hyperpolarized failure, while hyperkalemia pushes the voltage up into a hyperexcitable spastic crisis. Regardless of which way the scale tips, the microscopic transcellular gradient acts as the absolute fulcrum for your heart's stability. Any dyskalemia disrupts repolarization and warps the ECG. Recognizing those distinct electrical signatures early is the only way to intervene, proving that protecting that tiny 80 millimole fraction outside the cell is what keeps a patient alive. Preparation by Pharmaceutica.